Hello, good morning, good afternoon, good evening, everybody, wherever you might be. It is my great pleasure to welcome my collaborator and my former PhD student, MARIUSZ TOBOLSKI, who is currently in Wrocław, my hometown, and he will tell us about the contravariant functoriality of graph algebras. MARIUSZ, the floor is yours, the Zoom is yours, take it away.
Thank you, Piotr. It's always nice to give a talk at this seminar. And it's also very nice to be the last speaker for the calendar year. So this is like a summary. And also I thought that maybe the talk I'm going to give is kind of like a self-contained talk, which will not be very technical, at least I hope. So, so I'll go easy on you because we are already in holiday spirits and moods. So this talk is about contravariant functoriality of graph algebras. And this is something that we worked on with Piotr for many years now, for some time. And I'll start. I know that at the seminar we had already talks about this. There was a talk about by Jack Spielberg just few weeks ago on that seminar, and also Piotr given talks about it. I given a talk about this kind of topics and results, but let me still try to be self-contained, and I'll first start with all the motivations. Why do we're interested in this problem? And this is such a kind of a cute idea that we've got, and that was driving us, which turned out to be quite very fruitful. So let me start with motivation. Okay. And so we were interested in problems in non-commutative topology. And if you look at a very particular non-commutative space or a C-star algebra of that space, you look at the Podleś sphere, and then I always forget. I think the name should be equatorial Podleś sphere, because there's the standard one, which is the unitization of compact operators, and that would be I want to talk about the other one, the equatorial and Podleś sphere. Right, and this definition goes back. It's a Q deformation of a sphere, and this goes back to Podleś PhD thesis. And what he already discovered was this pullback structure for that C-star algebra. Okay, so we have the pullback structure. I'll tell you in a second. So this guy is in the templates algebra. And here we have the symbol map. And this is a pullback of C-star algebras. And that was proven already by Podleś. And independently, I assume, by Algebras. So this nice structure, this pullback structure for that C-star algebra, it's if you think about the templates algebra as the deformation of the disk, it just gives you the usual picture of gluing two disks over the boundary circle, right, to get the sphere, right? So this is like the non-commutative deformation of this picture, right? And this was known for a long time. Then Hong and Szymański well, they were interested in representing quantum spheres or other non-Q deformation spaces, Q deformed spaces as graph sister algebras. And what they found out is that this sister algebra, so this motivational part, I will not give you any definitions for now. I'll just draw some pictures, and so you'll see why we were interested in this. So, okay, so this is a graph, and I'll give you a definition of a graph, what I mean by a graph, but for now, this graph is we have some vertices and we have arrows, right? And so this sister algebra turns out to be isomorphic to the graph sister algebra of that particular graph. The Toeplitz algebra can be also realized as the graph sister algebra of such a graph, just two vertices, two edges, one. So this one is a loop, so I'm allowing loops in my graphs. And then also the functions on the circle also can be represented as a graph sister algebra. And the final picture of this pullback corresponds to, if you just draw the graphs, it looks like this. So that was the graph of the Potley sphere. This is the graph of the Toeplitz algebra. This is the graph of functions on a circle, right? And we have such a cute picture. And if you look at it, you see immediately that this is, well, even if what I will say now is very informal, that this is kind of like gluing those two graphs, right? Gluing this graph and this graph over this loop, and you get this graph. So this is like a push out of graphs. This is a very, like this is a particular example of a push out, because here all those maps are kind of, you can realize this as a subgraph here, right? And here again, so you have some injective maps, and you get this nice picture. And at first we were just wondering, okay, is it just a coincidence? And maybe there's some principle that one can abstract from this one example, right? So that's the whole idea. And the question that we're asking ourselves was, when do, and this will be like an informal kind of a question, because I'll not specify what I mean. I'm just giving you the idea, the first idea that we had. When do push-outs of graphs give rise to pullbacks of graph sister algebras? So that was the question that we had. Right, and now we have a kind of very general answer right now, but let me first maybe talk about, of course, to formalize this question, one would have to specify what is a push out of graphs, right? To write down like a category of graphs and to say that we consider push-outs in that particular category, right? And then in what sense those push-outs give rise to pullbacks. So there's some sort of, here if you look at this picture, the arrows goes this way and here they go that way. So there's some kind of contravariant functoriality involved. And this is something I'm going to talk today, right? So that was the question, and we started to think about it. And let me maybe very quickly go through previous work. I'll just give you the idea of, I guess this is some kind of standard, and I'll try to convince you that I'm not the only one who was interested in that question, and that there were some other mathematicians trying to solve these kind of problems. So first, we again can look back at the work of Hong and Szymański in a different paper they were looking at even quantum spheres, even dimensional quantum spheres. And those quantum spheres, they have a similar pattern. They can be, again, described as graph-sister algebras, and a very similar pullback structure, just really generalizing the one for the Podlesh sphere emerged. And then that was another indication for us that this might be a question worth looking into. That was that's 2008. And then there's another paper that at first we missed. And we missed it because it was dealing with some more general objects. That's Kunz-Pimsner algebras. And that was around 2011. Right? And what they were looking at pullbacks of Kunz-Pimsner algebras, but graph-sister algebras are particular examples. So if you look at C-star correspondences coming from row finite graphs, and again, I'm not going to be very precise with what I'm saying here. It's just like a PR part of my talk. If you will, if you just want a very quick remark, is that row finite graphs are graphs in which every vertex emits at most finitely many edges. Okay. And they've given the conditions such that such that, and here I'll use this name many times, two injective pushouts. What do I mean by two injective pushout? That both of the maps that define the pushout are injective. Turn to pullbacks. Okay, they've given these conditions, and you have to really read the paper to see that they were interested in this kind of a question, right? But maybe in a more general setting. But you can look it up, you can check the conditions, and they give some conditions such that pushouts will turn into pullbacks. But again, it has to be two injective, so the pullbacks are then two surjective, like on this first slide. Right here, these are all quotient maps. Okay. All right. And then there are two papers that we wrote with Piotr. And the first one was with Atabey Kaygun. And the second Sarah Reznikov. I don't know if I spelled her surname right. Piotr, can you help me with that?
I think you spelled it correctly.
Okay, thank you. And that was around 2018. And so that's what we try to do, is to make sense of this question and to write some answers. And we got some answers for arbitrary graphs. And we've given some conditions. But one thing we didn't do is we kind of well, in our conditions, we're trying to get rid of
breaking vertices.
Breaking vertices, yes, thank you. Right. And then a recent paper by Samantha Brooker and Jack Spielberg that is, well, they're talking about Toeplitz algebras, relative Toeplitz algebras. So these are also like graph sister algebras are example of relative templates algebras. And well, it goes both ways, but I don't want to go into that right now. But okay, so they were talking, they have, as they looked at our paper, and well, the similar question, the similar theme is still present, and they were able to add a condition on breaking vertices, right? So they dealt with breaking vertices. Okay, so we did it, well, more or less at the same time, but they were first to put in an archive. So that's another lesson, that you cannot wait too long with publishing your results. Okay, so this is the story so far, and I just wanted to highlight some of the papers that were dealing with this kind of a problem. And what I want to stress now is that all those papers, because you might think, okay, so well, breaking vertices are done. This sounded like it was, each paper was improving the preceding one, and that's true. And then this later paper is really improved our results by getting some conditions on the breaking vertices. But all those results talk about two injective pushouts. So basically about unions of graphs, right? Or just, like if you have a two injective pushout of sets, then this is just, you have two graphs and you glue them over their intersection. That's basically what happens. And we want to do more general things. So that's the main idea. So in this talk, we deal with just one injective pushouts. And that's the kind of improvement that I want to talk about. And then I'll tell you maybe two more general remarks, and I'll go into the actual part of the talk when I'll go very slowly from the very beginning of the definition of what a graph, what do I mean by a graph, to the result I'm interested in. So what was interesting for me when I was preparing that talk, I asked this question myself: what have we learned so far? Looking at all those papers, looking at the results that we got with Piotr, we learned the following thing, that this problem has, and this quotation mark, of course, because it's not a very formal statement, has nothing to do with analysis.
Yeah.
Right. So this is a purely algebraic problem. What you do is that you prove an algebraic version. You prove its algebraic version with no norms, no analysis, just some algebras and graphs involved.
It's kind of like K0, right? I mean, you don't
need. That's true. And that's, well, this is, we learned that from, because when we started here, maybe let me go here so here we have two papers, and one of them is purely algebraic, just talk about algebras that are associated to graphs, but they are not C-star algebras. And the other one was talking about C-star algebras, and we had like a very analogous results, that one was stated for just in the algebraic case, and the other one was in the C-star algebraic case. And it was kind of annoying because it seemed that this algebraic one should just imply the C-star algebraic. And then Alex Kirvasitu was interested in this, and he proved a theorem. So then after proving the algebraic version, you use Hirvasitu's theorem concerning the passage from pullbacks of star algebras to pullbacks of their C-star envelopes. Okay, and I'll state this result hopefully during the end of the talk, because there are, of course, it's not that for all star algebra, pullbacks of star algebras, you get pullbacks of their C-star envelopes. You have to have some conditions, and the conditions are always met for the cases that we deal with. So that's how you prove this. So the problem has nothing to do with analysis. That's why my talk will be really, for the whole talk will be really about algebra, and just at the end I'll invoke Alex's result to conclude the result for the graph C-star algebras. And I want to say something more. Okay, and what we also notice with Piotr is that the most general approach to the problem is to find a suitable subcategory of graphs.
Where sub refers to morphisms, not to objects.
Yes. Yes, so the objects will stay the same, and I'll this is when I will begin my talk, actually, right? So this is the last remark from this part that was just when I was trying to justify why I'm interested in that problem, and what is actually the problem, and what you have to do to prove results here. And now I'll start with defining the suitable subcategory of graphs, whereas Piotr mentioned the objects will stay the same, but we will change the morphisms. And we'll have such that we will get this contravariant functoriality of the, well, let's say, Leavitt path algebra construction, which is the algebraic counterpart of a graph C-star algebra. Okay, so let me begin this formal part. Let me start with category of graphs. So here by a graph, I'll always mean a quadruple where this set denotes the vertices. Here I have my edges, but my edges are directed. So I'm talking about directed graphs all the time. And I have my range and source maps.
Which make your edges directed.
Yes, exactly. So that's the range maps, that's the source map. Right? So the source is giving my edge its beginning and the range its end. Okay, so this goes from edges to vertices. Okay, so that's, and then all those pictures that I was drawing, that's how you always imagine graphs, right? You just draw some pictures, some arrows that are directed, and all those pictures, those graphs, these are examples of graphs. Now, these are my objects. So objects and my category are directed graphs. but usually I'll just forget about, I'll not say spell out directed all the time. By a graph, I mean a directed. So these are the objects, and I also, and I want to define morphisms. And these are in the literature, you can find them under the name of graph homomorphisms. Okay, so and what are those? So any graph homomorphism F that goes from a graph E to a graph F, this is actually a pair of morphism, pair of set theoretical maps F1 and F0. Right, so we have just the one map that goes from vertices to vertices, the other one goes from edges to edges, and they have to satisfy just one condition, well, maybe two conditions, so that the additional data that we have, so the range and source map, agree. So okay, so let me see if I maybe will not make a mistake here. Okay. And the same for the source. Okay, and this is your category of graphs. This is why in this talk I will just talk about category. When I talk about category of graphs, my objects are directed graphs and my morphisms are graph homomorphisms. Okay, so far so good. And now we want to change the morphisms, as I said. Okay, because so the graph homomorphisms, for the purposes of just pure graph theory, maybe there are enough, but for us, we need something more, and we'll have some additional conditions. So we'll talk about morphisms some more. And first, I'll define what do we mean by a proper morphism. So F here will always be, for this slide, this will be a graph homomorphism. And I define, I say that F is proper if both F0 and F1 are finite to 1. No, finite to 1, what do I mean by this? Just that for any, let's say, vertex, if I take the pre-image, this set is finite, and the same goes for this, where here this is a vertex for all vertices and for all edges. Okay, so that's what I mean by a proper homomorphism. And we'll this is our starting points. It's our starting point for those new morphisms. Okay, one thing to check is you can already just convince yourself that just a composition of proper graph homomorphisms is again a proper graph homomorphism. So we already have a subcategory of, let's say, some kind of subcategory when the objects are again directed graphs, but we want to have proper morphisms. Okay, now another condition which we call the target bijectivity condition. And this one is a little bit more complicated. And if let me maybe say this from the very beginning. If you look at those kind of conditions that I'm putting here, they might not seem natural from the point of view of just graph theory. Okay, and then so my whole the whole idea here is that we need them at the level of algebras associated with graphs. Okay? And then it all makes sense, I promise. So this condition is it goes as follows: that for any edge in the graph F, if I take the following map, which will start from the pre-image of X, and I take any edge here, and I associate its range.
Mariusz, sorry, I think I have one obvious correction. I think that we need not talk about surjections only. I mean, you can have that the pre-image is empty.
Oh, okay. Yeah, you're right. Yep. Yeah, you know what? It's.
I know where it comes from. I know why you made this mistake.
Yeah, that's true. But I just for a second, I was thinking about it when I was writing it down, but obviously not enough. You're right. So this, it could be empty. Could be empty, but the most important part is that it's finite.
Yes,
this
exactly.
is the important. Yeah, but thank you for that. So this will be, because this is a graph homomorphism, so this will naturally be here, right? Oh. And we want this map, right? This is a map from to be bijective. When this map is bijective. And I'll talk about it. I'll give you an example just in a second. But right now, let me maybe finish my list, my wish list of the things that I want to, the morphisms to satisfy. And the last condition is that F is regular. And it's regular F, and now the condition is that, well, okay, I'll have to tell you what regular vertices are first. Let me do it afterwards. Let me first write the condition. There's this mysterious reg of E here that I'll explain just in a second. Where a vertex is regular, and so this is a if and only if it emits something, but only finitely many edges, right? So this is, and I'm used to writing down both inequalities here, just as a sharp.
Yeah, that was the source of your mistake. Yes.
Yeah. So that's what it means to be regular vertex, right? So it's sometimes we call vertices that do not emit anything. Like sometimes that's, well, I don't know why I said that. So if the vertex does not emit anything, we call it a sink. If it emits infinitely many things, it's an infinite emitter, right? And the regular is anything in between. So this is our last condition of regularity. And then, well, okay, so this is then maybe a kind of a proposition. There's a statement that has to be proved. Maybe regularity is kind of straightforward to prove that if you, well, okay, that if you take two regular graph homomorphisms and you compose them, that you're gonna again get something regular. This is so for sure if it's true again, and the same is for target bijectivity. So, but you have to prove it. I'll not do it here, but because it's not extremely difficult. It's basic set theory, more or less. but you have to make sure that your conditions work and that you actually have a subcategory. And then we'll call, then we'll talk about admissible subcategory of graphs. And this admissible subcategory of graphs, again, the objects are directed graphs, but now we add all those, so objects, nothing has changed. So again, directed graphs. Morphisms, we take proper, so we add all of them together, proper, regular graph homomorphisms. Satisfying. The target bijectivity condition. Okay, so this is the category I want to talk about. And then, of course, well, you have to prove that this is actually a category, that it's a subcategory of the category of graphs. This is this is something that is maybe not entirely straightforward, but it's doable. And after that, you can think of some examples or counterexamples. Right? Of course, if you take a graph homomorphism that is injective, which means that both F0 and F1 are injective, well, then it's automatically proper, right? Because, well, one-to-one is in particular finite to one. Then if you, but what is interesting that not all injective graph homomorphisms will then be, let's say, let's satisfy target bijectivity condition. So this counterexample would be that just take a graph that is with just one vertex and you put it as a subgraph in this graph, right? So this does not satisfy target bijectivity condition. Let me write it like this, to be continued. Okay, so this is an injective morphism that does not satisfy this target bijectivity condition. So it's not that all injective morphism bijectivity will imply target bijectivity condition. Well, that's true. And now let me write some very nice examples of things that are not subgraphs, that are not injective. So if you have a graph like this, now we can fold it to this graph. Okay, and what do we do here is that those two vertices go to one, does this vertex, and those two edges goes to this edge, right? And this vertex go to this vertex. So this is something that we call folding. And this satisfies.
Sorry, Mariusz, can I ask?
Yes. Yes.
So your example which does not satisfy TBC, why?
Oh, sure. So let me go back to
the image
definition.
of your loop is empty, right?
Yes, exactly.
So
let me look. So first, I take any edge in F1. So there's this one edge. I take it, so this is empty, but then I look at the range of it, and the range is something, right? Because the range is here. So it's
okay.
Because I look at the range. Well, probably I wrote down something. Did I wrote down something wrong? Well,
But there are no edges, so there are no ranges.
Oh, yeah, you're right. Okay, so what is this?
I mean, for me, it's also suspicious. I mean, it should not be a counterexample.
It shouldn't be a counterexample.
No, because I mean, this is a very good morphism of graphs. I don't believe a target bijectivity condition would exclude it.
Oh,
okay,
yeah,
so
you're
let's
right.
go.
Of course. No. That's wrong, but it does not satisfy regularity, right?
Why?
Regular
Why?
was
Regularity was that the image of something that is not regular.
it's not regular.
It's not regular, and it is regular now, right?
Oh yes, you're right.
Yeah, okay. Yeah.
That's why I wanted to write. Yeah, sorry.
Yeah,
Oh,
okay,
of course.
okay.
This is what I wanted to have in my list.
Okay.
Mm-hmm.
Yeah, but
Okay.
thank you, because that was. If we have empty set here, if we have empty set here, well,
it's an empty set, right? Yeah.
This again empty, so everything is fine. Thank you for that. That was a mistake. Okay, so we can do this. So this is something interesting because that map is not injective map of graphs. So it goes beyond what was done in all the previous work and all the previous results. So this is actually the fun part, that now we can glue things in the graph, right? And then, however, this guy will not satisfy the target bijectivity condition. So we do the same, but now we fold. Now we fold here, right? So we put those two vertices to that vertex, and now this guy does not satisfy. Hopefully this time I'm right. Right? We can take a look. So we take this. The preimage of this set is now two. Of this edge is now two edges, right? And that's and those two edges end in just one vertex.
Yeah.
Okay. So now, these were some examples. So now you see what at the level of graphs. And now let me go to subgraphs, because if we look at what I was trying to tell you at the very beginning, that all those results that we had, even here, it's all the time talking about subgraphs. So injective graph morphisms. And now we can go beyond injective graph morphisms. So that's interesting. But now let me compare it. Let me maybe give you some conditions when an injective graph morphisms is actually a morphism in this admissible subcategory of graphs. Okay, so that's the next part. Next part is about subgraphs. So we can connect it to all the other results. So now I have, maybe I'll just, maybe I'll write it as a proposition. There is something to prove here. So we start with a injective graph homomorphism. Then F is an admissible morphism, or a morphism in an admissible category of graphs. I think maybe just write this for short. If and only if and now we have two conditions that have to be satisfied. One is something that in the graph C-star algebra literature is called saturatedness, which, let me just write it down. But with Piotr, we prefer this other way of writing down saturatedness. So if you're familiar with the graph C-star algebra literature, this might be strange to you, but it's the same thing. Okay, if we take a vertex that is regular and in the image of F0, I used subscripts so far. And this is a regular vertex in E. And so there does not exist a regular vertex such that the range of all the vertices, of all the edges emitted by this vertex is outside of that image. So now I should have stated superscripts. Now I'm struggling. Okay, so this would kind of say that this set, the subset of the set of vertices in F is saturated, right? So this is the condition. So it's really connected to saturated subsets. And then the second condition is something that we call.
Mariusz, let's maybe say it in words. So a vertex which would break the saturation property would be a vertex which would be a regular vertex in the subgraph and which would shoot all its arrows outside of the subgraph. That's not
thank you. Yeah, sure. Because sometimes it's much better to just say it in words instead of just writing symbols. Symbols are good for papers, but maybe not so much for talks. Okay, thank you very much. And now the other condition is that something we call the arrow condition, that if we take anything that ends in the subgraph or in the image of the subgraph, oh my. It should be contained in the image of F1 here, right? So this is the second condition. These are the two conditions that have to be satisfied so that this morphism is injective graph to be admissible. And here, this condition is that, okay, because we can, I'm still writing down those symbols, but if you think about just E being a subgraph, we can identify, because it's injective, E with its image here, right? So this means that anything that ends in the subgraph have to actually, or is that? Is that so? Have to start in the subgraph? Is that what I was trying to say?
I'm not sure you got it correctly. The thing is that if you have any arrow which ends in a vertex in a subgraph, okay, then this arrow must be in fact in the subgraph. So in other words, you cannot obtain a subgraph by deleting edges.
That's what it says.
Yeah,
that's what it says.
Oh, if that's what it says, then it's fine.
That's precisely what it says.
Okay. Yes, that was my impression too. That
I'm sorry.
That this is just this condition. But then I said it in, as you said, it's better to say it in words, and I said it in words. So yeah. But if you're giving a talk and
oh yes, of course,
staring at your screen, then sometimes I got confused. Okay, great. So this is the proposition that you can prove. So and what is great about it, that these are exactly the conditions from our from previous results. Let me call it like that. So this is from our previous papers with Piotr, when we only deal with injective morphisms. These were exactly the conditions. And if you will, I don't want to talk about it much, but in the graph C-star algebra literature, there is this notion of a quotient graph. And this is exactly the same, like it works the same. Instead of saying a quotient graph.
I'm sorry, guys, you were both wrong. The mistake is here. This must be E1. That's why I couldn't get it.
Oh yeah, of course, but otherwise it didn't make sense.
Didn't make sense, yes.
Yeah. Otherwise it didn't make sense. Yeah, thank you. Yeah. We all assume that I can So I guess we should assume that I can tell the domain and codomain of a map. Unfortunately, I missed that. But okay, but thank you. So now we have n-1 mistakes on this slide, and we can go on. So this part was just to connect with previous results. So now we know that our category is generalizing the thing we already had for injective graph homomorphisms, which is good. So now, what I want to talk about. I talked about these new possibilities, and okay, so let me go to Levy path algebras. Let me go to algebras. Okay, so this was whole like this was everything about graphs. I'll go back to graphs for the last part of the talk, but for now, for at least 3 slides, I'll now talk about algebras and associated to graphs. Okay, so are there any questions about this part with graphs only? We go those conditions. Yeah, here they are. Those conditions are when you look at the definitions of the graph algebras, you'll see that they were really tailored for those purposes. So now we want to talk about Levy path algebras. Okay. And now I'll write the definition just to be as succinct as possible. I'll write the definition as it is written in the Bible of Levy path algebras in the book by Gene Abrams, Pere Ara, and is that Mercedes Siles Molina? Maybe I said something incorrectly, but you know the book, you know what I'm talking about. And if you don't, then I recommend it. It's just called Levy path algebras, and that's Abrams, Ara. Okay, so now I want to talk about this definition of Levy path algebra, and what I'll do here is just you take a graph and then you define an algebra out of it. So E is an arbitrary graph. Okay, and then K, any field. So we'll talk about algebras over field K that I fix here. And now let us define the following set, F1 with a star. This is a set that gives you like another copy of your edge set. So these are just elements of this set will be denoted by E star for any E in E1, right? So any edge is getting a twin brother. Okay, and now Levy path algebra. Denoted LK of E of a graph E is the free. Okay, well, maybe write down over K to be very precise. Is the free associative algebra. Well, even better, K algebra generated by the set, and I take all the edges, all the vertices, the edges, and this new set that I just defined with a star, and well, subject to relations. And let me write down the relations for you. So the first relation for the elements given by the edges. So if I take two vertices, sorry, V and W, then their multiplication is the same as just taking the delta, Kronecker delta here times V, and that's for any vertex.
You mean any
Now,
VW?
For any VW, thank you.
Mhm.
And now I take the two. Now I have two conditions on edges that I'll call E1, E2. One of them is that if I have a source of a given edge and I multiply it with this edge, it's the same as just taking the edge multiplied with the range on the right, and this is the same as E for any edge here.
Yeah.
And now a little change. Now I'm telling you what's the source and target of this kind of element, because you can think about those star edges as kind of ghost edges going the other way. And so you impose this condition. And again, for any E in E1. And now the most important conditions that go back to Kunz and Krieger. The first one is that if I take two different edges and I multiply the starred edge by the non-starred edge, I get the Kronecker delta here and the range of that edge. And the second condition is that if I take a vertex that is regular, so it emits only finitely many edges, right? So the sum that I'm just writing, is finite. Then we have this last condition, the second Kunz-Krieger relation. Okay, so this is the whole definition. I know you can, so you can define it differently. You can start with a path algebra of a given graph, then to define extended graph, and then the Leavitt path algebra is exactly because the first three relations, they will come from the path algebra. And those first three relations come from path algebra, and then you will just impose those two, right? But I wanted to have it just on one slide and without invoking the path algebra. We'll only talk about Leavitt path algebras here. So that's the definition. Okay. And so now.
Yeah, but it's worth emphasizing that if you would restrict your attention just to these three relations and subject your free associative K algebra to them alone, you would get on the nose the path algebra.
Yes, exactly. Yeah, thank you. So, and of course, path algebras are interesting by their own, and they're used in classification of associative finite dimensional algebras with no additional structure. Okay, algebras. So here, what is nice about this definition is that for any field and actually any graph, sometimes just for the sake of most of the time, people assume that the graphs are countable, but for that definition, you don't need it. You can take an uncountable graph, and everything will work. So any graph, any field, and you get an associative K algebra like this. Okay, so now let me talk about the grading in paths, because it's a graded algebra, and that's really important for what will come next. Maybe. So let me here also be kind of short. So know that the assignments For vertices, I want my the degree of vertices to be 0. Then for edges, I want to get 1. And for the star edges, or sometimes called ghost edges, at least that's what they call it in the book, I get -1, right? And so when E is here, and I take E star here, that these assignments naturally extend to a Z grading on this out. And now how it's done, it's basically what you basically do, you have to take a look. So that's how you assign it a degree to elements that generate your algebra, right? This 0, 1, -1. Then to any monomial, you naturally just add up the degrees, right, of elements that constitute this monomial multiplicatively. And then you look at all the relations here. If you look at the relations, you see that what is happening, all of them are homogeneous with respect to that, right? So if you look at this thing, it's just like 0 plus 0, again 0. And here you have 0 plus 1, and you get 1. Here you have -1, 1, you get 0. And here also get a bunch of sum of zeros for this guy. Okay, so you're dividing by idea of generated by homogeneous elements. So it's a graded ideal. So first you have to, if you look at this associative free algebra generated by this, right? So the first part is very easy, how to define the grading on this free algebra. And then you check that those relations that you imposed still preserve this grading that are homogeneous. So that gives you the grading on path algebra or Levy path algebra. What is basically going on is that if we call a path of length n and sequence of edges, right, like this, well, sequence, you just write down edges. This is your multiplication in your algebra, right? The concatenation of words. So if you define path of length n to be such a sequence of n edges, then basically this grading is by lengths of paths in LK, right? And well, of course, I'll not go into the full theory of Levy path algebras, but you can find that any Levy path algebra is actually a span of certain elements. And you can define, you can say when, and then it's easy to define it for any element, to extend it to any element of the Levy path algebra. Okay, so this grading is important because there's a whole literature studying just grading Z-graded ideals of this algebra. And we use it extensively in our proofs. So, okay, let me now go to the first main part, this contravariant functoriality. And this is a theorem that we have. The theorem is as follows. If F is we take a morphism in the admissible category of graphs. Then the assignments. So now we start this way. So this has to be contravariant. So we start with the Levy path algebra of the graph F. We take any vertex here, and we map it to the following sum of these in the pre-image. Well, I'm messing up the S's and F's of F0 W, and this is V, and this is an L, K of E. And I'll call this assignment, I'll call this a pullback of the map F, because it really is a pullback here. If you look at it here, then for edges, maybe let me call it X. If I take any edge here, so that was for so here I take W from F0, I take X from F1, and he'll take X star from F1 star. So now I take all the edges in the pre-image, one of X, and write down E here, and here, just the same thing over and over again. For the star, I take again a sum. I'll still index this sum by this elements E, but I'll write down E star here. Okay, and these are all the assignments I want to have, and they give rise to a Z graded algebra homomorphs. Okay. Okay, and so I wanted to talk about the idea here. So that's the whole theorem, and this proves that we have this contravariant functoriality for this admissible category of graphs, right? And this is how we define this F star on the generators, and then we extend it by universality of this definition, right? This is a free associative algebra construction, so it's universal. The only thing we have to check is that the relations, the Leavitt-Path algebra relations for those images are satisfied, right? And this is where our, maybe very quickly, I will very quickly comment on the proof. So idea of the proof. So the relations here are will be satisfied. So we don't need any. The only thing we need here to prove those is that F is a proper graph homomorphs, and they will be true for any proper graph homomorphs. So what happens here is that, well, first of all, if you look at the definitions here, right, we want those sums to be finite. That's why we need properness. So otherwise, this is not even well defined. So if F0 and F1 are finite to 1, those sums are finite, and we get well-defined assignments. So then when we start checking those conditions, when are they? So V, E1, and E2, turns out we don't need anything more. Just proper graph homomorphisms is still enough. But now, okay, the CK1 condition. For this one, so the target bijectivity condition is exactly tailored so that this is satisfied. Okay, and this is just by checking the condition that it would be sufficient for that, we impose this condition. And then for the regularity, and then the regularity combined with the target bijectivity condition will give you the CK2. So let me write this down in this idea of the proof. So this is actually very once you get the right idea, it's kind of straightforward to check this. Right, so here we need target bijectivity condition plus regularity. And that's the whole proof. That's the whole idea of the proof. That's how you use all the pieces, how do you put them together to get this desired result. Because now we know that not only for subgraphs we can have those morphisms going the other directions from algebras, but also for any morphism that is in this admissible category of graphs. Okay, so let me maybe speed up a little bit. Now I'll go back to graphs, because the question was, remember that the question was pushouts to go from pushouts to pullbacks. Pushout to pullbacks using this construction. Right? So what are the conditions on the graphs? So that was the whole thing we want to talk about. Let me very quickly tell you what the pushout of graphs is. Pushout of graphs, it's if you have graph morphisms like that. One is F. Let's say this is G, and these are graph homomorphisms. Then you define the pushout first, just as you could guess how to define the pushout of graphs, is just to use the pushout construction from sets, right? So we first do the vertices, then we do the same for the edges. So these are just pushouts of sets, and then you define, using the universality of a pushout, appropriate range and source maps, right? So you define this object, and then you prove that this is indeed, that EGF is a categorical pushout, is a pushout in the category of graphs. Right, and because you can construct it always, then we see that this category of graphs, so directed graphs and graph homomorphism, is closed with respect to pushouts. Now, however, this admissible category of graphs
is not.
It's not closed with respect to pushout. And here you might think that there's something, maybe some subtleties going on, but it's really not. Already at this level, if you just look at the category of, well, let me just write it down as like this: sets plus finite to one maps. Already this is not closed with respect to pushout. Right, so this is when the difficulty appears. Not anywhere else. It's not like regularity or target bijectivity is spoiling your result. However, you can prove that in this category of sets and finite to one maps, that it's closed with respect to one injective pushouts. If one of the maps F or G is injective, then you get this pushout by construction. However, we did not check this, and I believe we just that if you do the same, just if one of the maps F or G is injective, and they are morphisms in the admissible category of graphs, that this construction will give you again a pushout, but in the admissible category of graphs. We did not check this. We conjecture that it's true. But and also I realized that I put it and on archive, I put it as a lemma without a proof. So we'll have to add it later on. Hopefully, fortunately, it does not affect the result that I want to tell you, because you can just start by saying, okay, so maybe this category is not close with respect to push-outs, but just let's start. Assume that I have a push-out of in this category, and will it give rise to a pullback at the level of Levitt-Graph algebras? That's the question. That's the theorem. And just before this theorem, there's one last thing. I wanted to talk about those breaking vertices. That I already, I started talking about them just at the very beginning as something that is annoying, and we did not first handle them in the first paper of Piotr and Sarah. But then it's not that the conditions I'll give you are very natural from the point of view of this whole reasoning, and they will be also equivalent to what Samantha and Jack have in their paper. But let me start with a definition. What do I mean by a breaking vertex? Okay. I don't want to make more mistakes. So again, we start with a graph. So graph, and then we define a subset. We take a distinguished subsets of vertices and then we say that a vertex, so V in E, is a breaking vertex with respect to H if and only if the following is true. So first of all, it's not in H, okay? Then it's an infinite emitter. So let me write it down like this. So it emits infinitely many edges. But at the same time, so in general, it emits infinitely many edges, but only finitely many of them land in H. Okay, so that's this intersection of two sets. Well, I said it wrong. Outside of H. Oh, I wanted to say outside of H. Right? This should be correct. So this is a breaking vertex is a vertex that if you think about graph C-star algebras in terms of, if you think about graph C-star algebras and definition of a quotient graph, these are the vertices that might not, so in the quotient they might not satisfy the Contravariant relations because there was no relation for this vertex in the first place, because this second Contravariant relation is just for regular vertices. So there's no relations for this vertex, but then you go to this to the subgraph, right, which is here, and then all of a sudden this new relation appears. So that's why those breaking vertices have to be taken into account, but only when you look really look at Levitt-Graph algebras. I don't think people studying just graphs or thinking about them. I might be wrong here, but I don't. So that's the definition, and we have will denote breaking vertices with respect to by this. So these are all the vertices such that V is a breaking vertex with respect to H. Okay, so I was really trying to be self-contained. So this is, so I got you, given you all the definitions needed to state the main result. And let me state the main result. I hope I still have some time. Yeah, I still have some time. Like 10 minutes, is that?
Yeah, 9 minutes.
9 minutes, great. 9.5, right? Because we started
9.5. Yes.
Yeah, but I'm almost. So this is the main theorem. Unfortunately, I'll not be able to give you a sketch of a proof, or maybe I'll talk a little bit about the proof, but at least I can state it, and you can see what kind of assumptions are needed for this to be true. And this is the most, I think this is the most general result we've come up with so far. So now we start with a push-out diagram. So we take a push-out diagram of graphs. And why not? Let me write down what those maps are. Let me give them names. So I have a push-out diagram. So let this be a push-out in the admissible category of graphs. And now we assume the following. The addition assumptions. One of the arrows here is injective, but only one of them, right? So we're not taking 2 injective push-outs, but 1 injective push-outs. So let's say F is injective.
I mean, we allow 2 injective push-outs, but
we allow them. Oh yeah, okay, yeah. But they doesn't have, not necessarily, like G can be non-injective when F is injective. So this is this kind of a generalization that we are able to get here. So, and let me emphasize once again that just looking for a suitable subcategory of the category of graphs, directed graphs, it was the right way to obtain this generalization, right? Because if we all the time would try to think about subgraphs, we would not get this result. So okay, so we assume that F is injective. This is really helpful for the proof. And then we have 2 additional assumptions. We assume that G0 restricted to the pre-image of the breaking vertices with respect to this subset. So okay, so this is, well, of course, I'm putting everything in the wrong places. Okay, we want, when we restrict to this, we want this to be injective. Right, of course, in pushouts, it's always true that if you restrict this map to the image of F, it's injective, right? And the same here. So this is just by definition of pushout. But now we're saying more, that we're saying that also when you're restricted to the pre-image of all the breaking vertices, you're still injective. And this is a crucial assumption for this to work. And the last condition, I'll write it down as this, but then I'll say it in words. We also want this to happen. Okay, this is the last condition. And now let me maybe say in words what this is. So this is the way to write down this condition such that the proof is just the best way to phrase it for the sake of the proof. But what this exactly means is that if you have those 2, right, of course, we have a push out here, right? So this set is just the union of images, right? If both the edge set and the vertex set is just the union of images of those things here, right? And then what we're saying is that there are no breaking vertices that would be both breaking vertices for this graph and for this graph. Right, so this is not allowed, and this is exactly the condition that was spelled out in the paper of Samantha and Jack. So this is a condition that is equivalent to it. That's what I'm trying to say. It might be not obvious, but okay, unfortunately, I don't have time to prove. And then we get a pullback at the level of Leavitt path algebras. Okay, so and here the maps are just those pullback maps that I defined for you. So everything on the slide was, I think, defined in the stock. So I'm really proud of myself. Be a pullback of, and this is important, of Z graded.
Mm-hmm. I think you need to say is a pullback and not be a pullback.
Yeah, it's a pullback. Yeah, thank you. K algebras. Okay, and then you can add some additional things that if about unitality. When this is unital, when we talk about graphs that are finite, with finitely many vertices. And because in the Leavitt path algebra, the unit is, if you have finitely many vertices, the unit is just the sum of those vertices. If you have infinitely many vertices, then the algebra is not unit. So this is the statement. This is what the most general statement of the sort, that when pushouts are turned into pullbacks by this Leavitt path algebra functor. And just very quickly, let me tell you that the proof. So first of all those proofs, the proving that something is a pullback of algebras, it's always the same. You have some conditions, right? This is if you have a commutative diagram of K algebras.
Sorry, Mariusz, let me interrupt.
Yes.
But I think here, don't you mean F0?
Yes.
Yeah, thank you.
Yes, of course. Because I said that about something happening both in E and in F, right?
Mm-hmm.
So that's yes. So there are no breaking vertices, like in P, there are no breaking vertices that are both with respect to E0 without the image of F and F0 without the image of G, right? So that's that's what is important here. Okay, thank you. Otherwise, it didn't make sense. So now this is the result, and the proof is just, you look. So first of all, to prove that's a commutative diagram of K algebras is, or even, well, let's say just abelian groups, just forget about all the other structure. First, you have to know that the kernels of those two maps are disjoint. No, just zero, well, disjoint, no, that they're the only, that the intersection of those kernels is just zero, nothing else, right? And this turns out to be equivalent to the fact that P is a sum of images here. So this one you get for free. Then there are two other conditions, one that you would prove. So this all follows, let's say, for example, Pedersen's paper on pullbacks, where he writes down a proposition when that commutative diagram of algebras is a pullback if and only if, and he gives some conditions. One of them is this intersection of kernels to be zero. There are two more conditions, and one of them is just prove we get for free if we assume that F is injected, right? And there's this one last condition that is concentrate about kernels, and kernels of those morphisms of these guys are graded ideals. You well, maybe have to prove it, but these preserve the grading. These are homomorphisms preserving the grading. So you have graded ideals, and there's a whole book and many papers about graded ideals and the Levitt path algebras. So you can just look at the results there, and then those two conditions are the ones that really give you this last condition of Pedersen. Right? So this is how the proof goes. So it's when you write down the right conditions, it's a straightforward proof. But first you have to come up with the actual the good category of graphs, and then you have to come up with those conditions. Right? But when you do this, the proof is just false. It's still kind of nasty. It's tedious because there's a lot of calculations involved for this last part, but it's still the idea is clear. And then the last thing I want to say, but I'm over time already. So maybe I'll just say in words that then if you have the result for Levitt path algebras, to go to graph C-star algebras, we use this result of Alex, and his result is just the conditions for Alex proof to be true is as follows. So if you have a pullback of star algebras that are Z graded, okay, and the zero part of the grading, so you have to know this, that the zero part, because we talk about star algebras, but they are universal C-star algebras, right? So you have the C-star envelope. And if we know that this part, the zero part of the grading of this top algebra is an AF algebra, okay? If we get an AF algebra, which is true for Levitt path algebras always, because so the fixed point subalgebra due to that you get from the gauge action is an AF algebra always. So this we always get for free. And the other condition is that one of those maps have to be onto, which is taking care of taking one of this map to be injected. And then pullback of those universal C-star algebras give rise to a pullback of the C-star completions of the C-star envelopes, right? So this is exactly graph C-star algebras that we're talking about. So with this very clean kind of like a much simpler proof, not invoking any analysis, actually we get a resultant analysis using the resultant PRC. Right? So, and this is the most general push out to pullback result for graph C-star algebras that we were able to get, and it's more than what was in the previous works, but also it's maybe not less, but it's I don't want to say that we really generalize everything that are in the papers of, say, Robertson and Szymański or Brucker and Spielberg, because they also dealt with different objects. For Robertson and Szymański, they were dealing with Kunz-Pimsner algebras. So the next step would be to generalize it maybe to Kunz-Pimsner algebras in this way. I don't know how that would look. I think that Alex Frey, he had some results of this sort that he proved. So that would be interesting to see. And the Teplitz algebras, well, every Teplitz algebra is actually Levitt path algebra of a different graph. But well, Teplitz algebras corresponds to things called Cohen path algebras. Sorry, not Cohen. Cohen path algebras, but it's Paul Moritz Kohn.
Yes.
And every relative Kohn path algebra is a Levitt path algebra of a different graph. So we're still kind of not missing anything from this perspective. But if you work with those relative things, it's still like a different category. You have like objects are pairs and stuff like that. So there's still something more in the paper of Brucker and Spielberg. But as far as just graph C-star algebras goes, this is the most important. This is the most important. This is the most general result. It's very important to me. That's why that was the slip of a tongue there. Okay, thank you very much for your attention. And
Okay, Mariusz, thank you so much. Before we go with a round of questions, please allow me to have a go. So first, I really would like everybody to appreciate that in general, completions and pullbacks do not commute. Okay, so the result of Kirvasitu is substantial. I mean, it's you cannot, it's just blatantly false without any assumptions. And I usually give such an example. If you would like to glue two circles over an arc, yeah, so there's some arc, not just a point. Then if you do it in the category of some polynomial algebras, well, the moment you know a polynomial type function on infinitely many points, you know it everywhere. So gluing polynomial algebras on circles will give you a polynomial algebra on one circle. But of course, if you do continuous functions, you'll have then continuous functions on a figure 8, which is not one circle. So that's really substantial. You should not take it for granted that the pullback of completions coincide with the completion of a pullback. And that's basically what Alex's result is about. Second thing, now, Mariusz, what I would like you to say, to give some examples. So first, for starters, note that this one injectivity assumption is not so devastating as you might think, because in order to use Meyer-Vittori's technology, in order to use, I don't know, 6-term exact sequence in K-theory, you need one surjectivity in algebras, which comes from one injectivity on graphs. So this one injectivity is something important anyway, otherwise you cannot apply such crucial Meyer-Vittori's tools. So I would like you to show some examples where really you must go in real life beyond union of graphs, okay? It's really natural to have some push-outs which are not just unions of graphs, and this generalization that we have here handles these important natural examples. So I'd like you to say this, but before you do, I'm kind of, please correct me if I'm wrong, but I'm kind of puzzled by this condition because, well, number two, I understand, because basically what you are doing, you are saying that yes, it's true, G need not be injective, but at least we do not allow to glue breaking vertices, right? I mean, breaking vertices for F must not be glued. And here, because F is an injection, you can basically forget this. It's just a subset. Sure. But here I'm kind of puzzled because what you are writing on the left-hand side is that I take I take breaking vertices for E, and when I map them into F, I have also breaking vertices. And I thought that what we are saying is that breaking vertices for E cannot be breaking vertices for F. So I'm kind of having troubles to reconcile. Please enlighten me.
Yes, that's true, but it's okay. So, as I said when I was giving this condition, it's at least for me, I know you can look through to our paper to see it, but at least for me, this is the best way to formulate what you just said. Then you have to prove that it's equivalent to this, that the breaking vertices for E are not breaking vertices for F. But here, notice that what we look at is we look at breaking vertices with respect to this set, right? Yes. Without so it's not for E, it's like breaking vertices for E without the image here. We just don't want these kind of breaking. We want that if I take the pre-image of that breaking vertex, that it's again a breaking vertex here. And if you write down the kernel of this map, well, let's say probably this one. If you write down the kernel here, you exactly want to have that this set is here. And then I had a proof, but I don't just like on the top of my head, I'll not be able to write it down. But I have a proof. If you want, we can talk about it, and you can prove that this is actually equivalent. Checked it several times, but yeah. But for now, I'm really, I don't remember how it goes.
Okay, I believe it. Just slightly confusing because
Yeah, sure. Yeah. I know. Maybe I should. So if you want, you just change this to the condition that you don't have breaking vertices that both for E and both for F.
Yeah, so you can simplify it and say, let's consider that both are injections and you are really talking unions of graphs, yes. So you don't have these G's and F's floating around. And basically, when you have this union of graphs, okay, so you have your G in the middle, this is your G. And when you are talking, so this is your E, and this is your F.
Yes.
So when I say a breaking vertex for E, I mean a vertex in G, which is a breaking vertex for E less G. And I say breaking vertex for F, I mean a vertex in G, which is a breaking vertex for F minus G. Okay, so basically somehow here what you are saying is when you delete these functions is that the set of breaking vertices for E is containing a set of breaking vertices for F, and that's confusing for me. But
so yeah, but see that this is the breaking vertices for this. They are not. Okay.
So my inclination would be here to write that the intersection is empty. That's somehow what I would write.
Okay, that's what you would think. Okay. Yeah. Okay. Yeah, I'm pretty much sure though that this is the condition that we need, but maybe I.
But okay, it's a technicality.
Yeah,
there is a condition which is the same as the condition Samantha and Jack derived, and that's it. So now please show some examples which are not too injective.
Well, so basically, but I don't know, like real life examples that I can. Well, just. The only thing that really changes now is that instead of union of graphs, I can now take a graph. So I can take. So what I was trying to think of were those kind of foldings.
Yes, exactly.
That would happen.
Yes. That's what I had in mind. Yes.
Yeah. Yeah, remember I had some, I don't know why, but I didn't prepare the examples for today. And I don't know if I just now trying to figure it out if I will succeed in the end.
Yeah, probably.
So the only thing that really changes is that, so on one hand, okay, I have this a subgraph, I take a subgraph here, but here I can fold some, if in this graph G, I have things like that, right? I can now fold it and get a graph which is just looks exactly the same as G, but with this one folded. And then, well, I have to make sure that this is still a graph morphism, but now I can do those kind of things. And then in the push out, I'll not get the union, because some of the things will here be glued. I think that's the only thing I can. But so I think here what is really important is that
yes.
Now you don't have to only talk about injective morphisms, and that you can take any one injective morphism and or push out of graphs. And well, I think if we would have enough time, we'll cook up a lot of examples that would be actually interesting, and I think this is something to do also on our list, I would say, for the paper.
Yeah, but you answered my question. I mean, and of course, you can have finitely many. I mean, it doesn't have to be 2. You can have 3 or 5, whatever.
Yes.
So that's also quite all right, because you must ensure this target bijectivity condition. That's quite essential.
Yeah. So let's say you could embed a Podlesh sphere graph in some bigger graph. So your G would be your Podlesh sphere, and then if you would embed it in some bigger graph, but for this one map here for F, you would fold it to get a Toeplitz algebra.
Yeah, exactly.
Right. So here you'd glue the Toeplitz algebra with this bigger graph this way.
And this would be admissible now?
Yes. This would be an admissible morphism.
So this means that we have a map from the Toeplitz algebra to the Podlesh sphere, right? The equatorial Podlesh sphere.
Yes. I think there's nothing wrong with that.
Yeah, because it's a pullback of two Toeplitz algebras.
Yeah, so easy we can embed it like into two different ways.
Yeah. Okay. And this is already very, very natural geometrically, okay? Okay, so any other questions or comments? Tomek, you wanted to ask something.
Yes. So first of all, I would like to say that there's a question on chat.
Oh,
okay.
About this pushouts. So I share this confusion from the chat because you said that this category of admissible morphisms is not closed. You said something like this, closed with respect to this.
So this is exactly what I mean. Not closed with respect to pushout means that the usual construction does not give a categorical pushout. Exactly. This is what I meant.
So in your main theorem, the right proper formulation should be that you have a diagram, you have a square satisfying some conditions in this subcategory, which is in addition a pushout in this category of graphs.
Yes. So this is why I'm what I have here. Right. This is that. It's a pushout in the admissible category. So I have this diagram, which is all. So this is diagram in the category of this admissible category, which is a pushout, like a categorical pushout.
But in this ambient category of graphs, it's not a pushout in the admissible category of graphs.
It is, but I'm just saying. I'm assuming it is. I'm not saying that I can always construct for any pair. Yeah. So I'm just saying, assume that I have a pushout. So this is my way out because I think for one injective pushouts, it should still be true. But I was trying to prove it today, and somehow I got nowhere with that. But I think it still, if you assume target bijectivity and regularity of F and G. So now assume you have just two morphisms, F and G, right? And then you assume that they satisfy target bijectivity and the regularity. And also these conditions are independent of each other. That was also a question in the chat. That's true. There's no, and I was trying to show it in those examples, but that wasn't too enlightening. So now assume that they are in the category of admissible, in this admissible category, and one of them is injective, and then I would conjecture that then the usual construction of a pushout of graphs will yield a pushout in this category of admissible graphs. That these maps are again satisfy the target bijectivity and regularity.
But can you prove it?
So yes, so this is something I was trying to do today, but just today I forgot about it. We started to do other projects with Piotr, and I forgot that this is a thing we still have to figure out. So as a way out for this theorem, I'm saying assume that I have a pushout, and this is and of course there are, in many cases it will be a pushout, and there are pushouts in that category. It's not that for every, for example, if they are both injective, there's no problem, right?
Okay, so let's assume that F and G are admissible. Is it then automatic that IE and IF must be admissible as well?
So it's not automatic. I would not say so.
But you can prove it.
Yeah, I think you would have, it would be a combination. You have to use both target bijectivity and regularity all the time to prove this. But I would be surprised if that doesn't hold. But yeah, I didn't prove it. So I'm assuming that I have a push out in this category. And then I know that this functor will give me a pullback. But first I assume that there is a push out. And of course, in those kind of easy examples, well, you can cook up many examples when this will be the case. And so the problem is that is for every, if I take any pair of morphisms, well, I always, the construction will give me a categorical push out, and this I don't know. But it's not like the theorem now is empty, right? Because I'm assuming something that cannot be satisfied. It's satisfied in many examples. So you can assume that you have a push out, but I didn't prove yet that this category is closed with respect to one injective push out, by which I means assume that F is injective and both F and G are admissible. And this should imply that E and F are admissible.
But
it implies that they're proper.
It is not about closedness.
Mm-hmm.
Closedness doesn't make sense here. It's a question whether the push out in the ambient category
mm-hmm.
restricted to subcategory coincides with the push out in a smaller category.
Mm-hmm. Okay, so
because a priori, if you say that this triple IE, IF, and P is a push out in the admissible category, if you don't know how push outs look like in this category, how can you even apply this Levitt path algebra construction to this? Because if P is not for instance, the push out, the algebra corresponding to push out in the category of graphs, what's the meaning of LK of P?
Yeah, if that's well, it is a graph. Well, in this ambient category, as you said, there exists a push out like that, and I know what P is, so I know what the Levitt path algebra of P is. But so the actual question is does that restrict from this push out construct, the usual push construction? If I restrict it to the subcategory, do they again get a push out in the categorical sense? That's what. Yeah.
So my problem is that in this subcategory, an honest push out could be very, very strange, having nothing to do with the push out in the category of graphs.
Yeah, a priori, yes, but I doubt it. But I don't have a proof, so
okay.
I don't know.
Thank you.
So let me weigh in to somehow just. Can you give me some blank, Mariusz?
Yes, please.
Yeah. Okay. So what we really wanted was the following: if you take really this full category of graphs, then it admits push outs. And the categorical push-out coincides with simply assembling push-outs of sets. Okay, you can prove it. It's just very boring diagram chasing, and we did it in class. So the construction which comes from set theory, which you would expect as your natural suspect, is really gives you a categorical push-out in this full ambient category of all graphs. So now we asked ourselves the following question. I take two morphisms of graphs, E and F, and of course, they admit a push out in this ambient category. Okay, so there is P, and you can complete it into a push out diagram. Okay, but now in order to induce pullbacks on Levitt path algebras, well, we needed to assume that these morphisms are admissible. Otherwise, you don't have pullback maps going from LKF to LKG and from LKE to LKG, okay?
You know what LK of P is, but you don't know what's the map.
Exactly. I mean, the map may not simply exist, okay? Yeah, thank you, Richard. So you know, I don't have a pen here. I'm writing with a mouse. That's why it's so clumsy. But please bear with me. Okay. So this is why we needed these extra assumptions. But you can immediately convince yourself, and Mariusz very beautifully pointed to the reason why it happens. Is that if you assume these two maps to be admissible, these two morphisms to be admissible, by no means these always existing maps here, because push-out does exist in the ambient category, these maps in general are not admissible. And in particular, what fails, that if even if both of these maps are finite to 1, then in general, the push-out will produce a map that one of these maps here is infinite to 1, okay? This is what happens in set theory, all right? So that's an issue, but this issue is resolved if you assume that at least one of these morphisms here is not only admissible, but actually injective, okay? And when you assume this, I believe, so this is definitely what we should prove, Mariusz, that if you assume this, then these morphisms that are naturally induced in the ambient category of graphs, okay, so that you look at categorical push-out in the ambient category of graphs, that if these two maps defining the push-out are admissible, and at least one of them is injective, then these two maps are also admissible. And in fact, this map is also injective. Yeah,
yes, exactly. That's
the whole story.
Mm-hmm.
That's what we really wanted to say.
Yeah, and I was trying to it shouldn't be. I think there's a good chance that this is true. For example, if this one of the maps is injective, then target bijectivity really simplifies, because now it's
yeah.
Pre-images of injective maps just consists of single elements, and then the bijectivity. This shouldn't be hard. So like proving that this injective map satisfies target bijectivity should be easy, and then I think it's like this: like if one satisfies target bijectivity, the other have to. There will be some kind of a interplay between those two, and the same for regularity. I think if one of them is regular, then the other have to be regular. Otherwise, you get some stupid contradictions. But so what I was struggling to prove today, but for a few hours, was actually to prove this regularity, and I think that there's a chance that it's true, but I just couldn't do it.
So if you want to be really precise with the formulation of our theorem, what we assume is that we have a push-out diagram in the category of graphs, and we assume that these two morphisms are admissible, and one of them is injective. Then
to be very, I now understand that. I wasn't really precise, because when I said that, let this be a push-out in this category, and then, well, okay, but we don't know how those push-outs look like. So
exactly, yeah.
It's just a push-out in the admin category, and then we assume that it is also, it turns out to be all, the maps in this, giving you a push-out in the ambient category are also admissible. Right, so this is the assumption of the theorem. Yeah, thank you for that.
And hopefully we need not assume that these are admissible. It should follow from the admissibility of these defining ones and injectivity of one of them.
Yeah, hopefully. But I think actually we got, I don't know if you saw, but we got an email from someone asking about this as well. I never got to answer that email.
Okay.
Yeah, because
okay,
there was no proof.
Else?
Yeah, in the archive. Yeah.
Okay, I don't see any other questions or comments. So, Mariusz, thank you again.
Thank you.
We're very happy to listen to this presentation. Of course, I'm biased because it's also my work, but I think that everybody should appreciate how easy it was to follow, because you really kept your promise on being easy for us. So this was a very holiday-like talk. I appreciate it. And you see, the benefit of this approach is that basically all the way through your talk, nobody escaped your talk. I mean, people stayed until the end, until the questions. So,
yes, actually, yeah, the most work I did was for the presentation, because the results themselves, I even like maybe I could do more on actual formulation of the results than just to make it. But okay.
Okay, so let me stop recording.